for joining us this morning for another year of the Michigan Space Grant Consortium. One of the reasons that I'm very enthusiastic about Space Grant is not only that JPL and NASA work with all of these universities and students and faculty from around the nation all the time, but back in 2008, I received funding for an internship with JPL through Michigan Space Grant Consortium. And I was just looking at the timeline, and 10 years after that internship, I was leading 2 spacecraft as we were approaching Mars at JPL as well. So Michigan Space Grant certainly gave me opportunities, which then started me on my career as well. And I hope it does the same for you, and that you continue to explore space, whether it is through the state of Michigan or elsewhere in the US or around the world. Today, though, I wanted to speak to you a little bit about what we're doing in what might seem to be a little bit of an offset from space, and that is diving deep into the ocean on here and seeing what we can do here on Earth in order to start to explore worlds beyond our own. Our planet is a wonderful water world. We actually consider it to be one of the ocean worlds that is out there. And just beneath the surface, you get teeming life, whether it's from the corals or the kelps that might be out there, or even just the animals that live just beneath the ice itself. So around the world, around all the different types of waters that we have, from freshwater to saltwater and such, we find that often life tends to thrive in these ocean environments. And so as we search for life beyond our own world, we tend to look for areas that might have water, might have had water in the past. Whether that is driving our exploration of Mars, or if we're looking directly for, as I said, ocean worlds elsewhere, water seems to be a location where we would have some significant scientific interest. And as we explore into our own solar system, we've identified that there are a number of different moons out there that are also representative of ocean worlds, whether that's Europa with its kilometers of ice followed by up to a 100-kilometer ocean on its surface, Titan with its methane lakes on there, and many more that have all sorts of different features that yet let us classify them as ocean worlds. We are not unique here on Earth with having the sole water in the solar system itself. But if there's more water that is out there, could there be more life, or at least biosignatures and signs of life beyond our own world? One of the most promising locations and perhaps best examples of what an ocean world might look like is Europa, a moon of Jupiter. And here there's a thin shell of ice. Now that thin shell is still up to potentially 10 kilometers thick of ice, but based on seismic activity and gravity stressing of the planet itself from Jupiter, we think there's enough warmth that underneath this icy shell is an ocean up to 100 kilometers deep. Now that is a significant amount of water, and because this moon is of course smaller than the Earth itself, even though it's 100 kilometers deep, the pressures at the bottom of the ocean are about equivalent to what we might expect at the bottom of our own Mariana Trench, one of the deepest spots in the world on Earth for our own ocean on here. So if we were to explore an ocean world like Europa, or even many of the others, you might consider that there are a few different ways that we would want to take a look at it. There is the remote sensing, the passing by overhead, say with Europa Clipper that we're hoping to launch within the next several years on here, headed out to Europa to do a survey of the surface. We might use Europa Lander to reach down and touch the surface itself, perhaps digging in tens of centimeters in order to try and analyze first samples. Or perhaps we can use the crevasses and the potential passageways to the surface in order to send down a cryobot to try and survey what happens within the ice. Should we make it through the kilometers of ice, we can begin to explore underneath with something like the Buoyant rover, or even down into the depths of the water itself with something such as the Nereus Under Ice Explorer. So for each of the different regimes that we might encounter on an ocean world, there are different types of vehicles that we might need to develop. And perhaps there is analog testing we can do here on Earth to learn better about how we can explore, and not only about what we should send to explore on this moon. But the Earth itself is a beautiful ocean world. It provides us ample room for analog exploration. With this planet that we have, with this wonderful globe of water, we need to start to explore where we would try and test out our different vehicles and how we can learn so that we can explore beyond our own world. Now, this presentation in some ways is a play in 3-act on here, and I would encourage you to think of 3 different themes as we're going throughout this. It's not only that we're trying to explore these ocean worlds beyond our own, but think about exploration in general. And in this case, think about how failure can motivate opportunities. Think about how to change your thinking and look at things from a different perspective. And as we're trying to do with these small spacecraft, I'll try and convince you that small is not necessarily less, but it provides you a new way of exploring around. Let's go back to, as Mark said, the before times. Last October, when we were out on a icebreaker north of Norway, seeking to understand hydrothermal vents at the bottom of the ocean. Now, these hydrothermal vents have only recently been identified back in 2016 and only into a general area. But in this particular trip, we took an icebreaker up there to try and send a remotely operated vehicle, an ROV, down to the bottom of the ocean, 4,000 meters down, in order to take samples of the hydrothermal vents themselves. Now, this is the size of the icebreaker, the Crown Prince Haakon, and you can actually see this little orange dot over here. That's actually the ROV that's being lowered off the back end by a very large crane. This is a quite large ship. You can see the helicopter landing pad up front. And so this ROV is not exactly small when you can see it from this perspective on here. And in fact, when it goes underneath the ice, the ROV is large enough to carry a host of different payloads. It has a robotic arm on board that allows it to go out and collect samples of sponges or other things on the bottom of the sea. It has a number of lights, and as you can see, it actually opens up its front to expose these payloads and scientific instruments to the broader world that we are trying to explore. Now, NUI, or the Nearest Under Ice Explorer, provided by Woods Hole Oceanographic Institution, is a premier submersible designed to go out on a fiber optic tether to extend its reach kilometers away from the mothership hovering overhead. It has batteries on board and is able to explore both in an autonomous or a remotely operated mode, and it is an ideal vehicle to explore underneath the ice itself. On this fateful day, the rover was extended down into the ocean, seeking to find those hydrothermal vents some 4,000 meters below. It did proceed down after a number of kind of false starts along the way where we had trouble with the ice on the surface. And as it reached the bottom of the ocean, suddenly, and only 20 meters away from where we actually were to encounter the vents, the vehicle stopped responding. We have a vehicle trapped in the bottom of the ocean, a multi-million-dollar vehicle, and at this point, there is no way for it to actually reach the surface itself. The tether that it is on is only a hair-thin fiber optic cable. There's nothing that we can pull on there in order to bring it back up. And there is no way that it will actually come back up on its own if it can't actually hear our commands. So we're trapped in the middle of the Arctic, locked within an ice floe, and our vehicle down at the bottom of the ocean. We do have another vehicle on board. This one's called OPHOBES, and it is essentially a large camera hanging on a pendulum weight. The weight itself, these are solid steel bars all around it, and it's partially for protection and partially so that they can lower this thing like a pendulum below the ship. And the camera in the center of it allows us to get live views of the bottom, both video and still images there, a very high resolution camera. And with this camera, we're able to sweep across the bottom, looking for where we might be able to find Nereus. Well, along the way, we had the idea, could we put a hook on this vehicle and try and snatch up the ocean explorer that we have trapped at the bottom there? And we came up with the idea of, could we make a smart hook that's on board? And so I'd like to introduce you to SpongeBob Spare Parts, which was our attempt to take spare parts on board, everything from cable ties that you see up front here, to tearing apart other ROVs, commercial ROVs that we had that were used for surface work, and trying to adapt their equipment for much, much deeper pressure or deeper depths and higher pressures, to cable straps and other spare pieces that we had around. Even the flames that you see on the side are really just cut up electrical tape in order to make this work on here. But over the course of 3 days, a combined team of engineers from Woods Hole, from AWI, and from JPL put together a vehicle out of spare parts to try and rescue this multi-million-dollar vessel at the bottom of the ocean. Now, this vehicle would hang below OFOBs, hang below our imager, would provide just enough mobility to move around and try and direct a smart hook up front here so that we could latch onto NUI and try and bring it and then tow it back up to the surface. Without knowing exactly what was going on with the deeper under ice explorer, we had to rely on a mechanical snatch and grab in order to try and bring it back up. The question was, would a robot made out of commercial and spare parts actually work? So you can see the scale of this robot compared to that much larger vehicle over on the left there. SpongeBob was only about a foot in its longest length on the foam block that you can see at the top there. And we had a bit of fun with the eyes on board, but it really conveys the uncertainty that we had with regard to this vehicle and what we were about to attempt to do, lowering it down 4,000 meters below. As we went onto the ice-covered decks, SpongeBob hitched a ride on OFOBS itself for its descent down to the bottom. And as it's going over the edge here, you can tell that we're only on a short cable. We have a very short leash that we're able to move around, but that flexibility gives us just enough room that we might be able to grab the NUI vehicle below. Upon its descent, we of course have to dodge all of the ice along the way. And once we're into the water, we get a fantastic view of SpongeBob itself as we're going down. Now, the day we completed the build of this little rover on here, it turned out that the drop weights, the backup mechanism that we had to bring NUI to the surface, finally released. The drop weights are basically a set of steel plates that are on board. They're held by what we call a galvanic loop, in that over time, salt water will actually cause this cable to degrade, loosening the weights from the vehicle and causing it to come up based on a chemical reaction rather than a commanded reaction. And we can size the loops to let go after a preset amount of time, at least to a few hours or so. The problem with these weights was that they were supposed to release within 24 hours, and within 4 days, they still hadn't let go. So right around the time when we were ready to perform this first test, it turned out that those weights did let go on there. We had a vessel full of scientists and engineers that were dedicated to the exploration of the ocean depths. So we had actually been performing experiments. And what we had found was that we thought the galvanic loop was actually trapped in the mud below the vessel. And in the mud, there was actually a slowdown in this degradation of a loop. And so it took more time than we expected for the vehicle to come back up. Based on the experiments, we were never quite sure if it was going to come up. But since finally it let go, fortunately or unfortunately, we were able to recover the NUI vehicle itself, but unfortunately it wasn't able to be done through a test of our little Explorer. Well, we decided to test our Explorer anyway to try and prove that could we build something with these spare parts to enable a new realm of miniaturized exploration, rather than relying on monolithic, very large explorers that require an icebreaker to go in and drop down. Could we bring something that would be in a backpack and let almost anybody go out and explore beneath the ice? So at 4,000 meters depth, we began to control our Explorer with a fairly crude system for remotely operating it, and yet it worked perfectly. We spent hours down at the bottom, and along the way we let a number of different scientists control the vehicle themselves rather than through a full operational team here, because this vehicle was cheap. It was okay if we screwed up, if something went wrong in here. This was a demonstration. And one of the things we found was the importance of giving scientists the joystick, of allowing them to go directly after the targets that they might be seeking. And many tried to grab sponges off the bottom and bring up samples along the way. But it sparked the idea of, if we could do something smaller, how might we actually be able to take this forward and enable more scientists and more explorers to go forward? Or how, if our vehicle is that much smaller, could we get an initial payload out to a moon like Europa and start descending through the ice? So part one. Miniaturized exploration was an enabling feature to try and allow us to rescue the nearest under ice explorer. But what else could miniaturized exploration actually give us when we're trying to explore on an ocean world itself? We know on ocean worlds that there may be a layer of ice above us, and that underneath that ice is a lot of water. But when we look at where we find life along the way, here on Earth, we often find that life adheres to interfaces. In this case, the ice-water interface, where algae and microbes and other things like to anchor down and attach rather than be free-floating. So the next explorer, I invite you to invert your thinking, if you will. Think about how to explore that ice-water interface if we were to head out to an ocean world. On Europa itself, as I mentioned, there are a number of cracks and crevasses across the surface, all of these streaks on here. And we believe that these are areas where there has been an upwelling of water through broken ice, and perhaps also a passageway down to the bottom. And if we look beneath that ice, in this case, this photo is from Antarctica, you can see it's just as I described. Microbes, algae, life forms that are actually attaching to the ice surface on here, in addition to the abundance of life that is swimming around in the water just below. And as we start to explore, as we come up across in this case, the edge of the ice, you can see a host of light, and yet our animals and such are staying underneath the ice where they are shaded more, away from the light, but with direct access to all of the life that is just above them. If we take an up-close look at the ice surface itself, you can see the reason that the animals are staying in this area is that they're actually feeding on the algae and the microbes that are attached to the ice surface. This ice surface provides a structure for anchoring. And with that, we have this explosive growth of life under here. And it serves not only as a food source, but as a place where various gases and such mix, better feeding the photosynthetic process that we've seen down here. And actually, because it is a photosynthetic process, we've analyzed and found that many of the bubbles that you see on the bottom here are not just gases bubbling up from below, but they're actually oxygen that's being produced on the underside of the ice, creating our own little unique ecosystem up against the ice itself. And we'll find areas where these animals, these fish, will actually leave eggs and such trapped against the ice and protected somewhat from the broader ocean environment. So if only we could get an up close and personal view of what the under ice surface might be like. And the vehicle that we propose and that we'll be speaking about in this segment is called the Buoyant Rover for Under Ice Exploration. And this is the view that it achieves when it is going around and exploring the under ice surface. Just up ahead, you can see that there is a torn up area of the algae here. This is, we went to explore this area with a small little submersible, just as this one. And as the submersible approached the ice to get a closer look with its cameras, you can see that the thrusters on board actually ruin exactly what it is trying to look at. So if we want to explore this area to get an up close and microscopic view of the ice, we need an explorer that will do so without having the thrusters that will cause some destruction. We need a vehicle that is able to explore in almost this native environment and still allow us to achieve our observations. Well, last year we took an expedition down to Casey Station, Antarctica, some 66 degrees south. And this was a long way away from Europa. But in the pointer sign that was there, we certainly had to indicate where we were hoping to head next with our various vehicles. And you can see our attempt at a pointer down below. Now, Casey is a fantastic environment. And not only do we have the under ice exploration that we were able to achieve, but we had the wonderful wildlife and the support of the Australians to the Australian Antarctic Division on this particular trip. But in front of you, you have the Buoyant Rover for Under Ice Exploration, a unique vehicle that is designed not to rove on the bottom side of the ocean, but to float, to drive on the underside of the ice, providing it a constant anchoring point for the vehicle itself amongst the algae, the microbes, and all the other animal life that we see. And hopefully a unique vantage point for us to look carefully at that under ice environment. Now, we deployed not only at Casey Station and just off in the wharf, but in nearby areas as well. And you can see on the right an external view of how the rover moves on the underside of the ice. It has two wheels and a tail that prevents it from actually rotating around, But even as it drives underneath, very little impact is being pressed upon the algae and the microbes down below. And the tail provides us also an additional vantage point to attach instruments and custom tools in order to get a very close look at the algae. And sometimes we even take samples of it underneath there. We tested this vehicle also nearby at O'Brien's Bay, and were able to cut holes in the ice to actually deploy the vehicle and compare it to what we might see with our other instrumentation that would traditionally be sent down through a through hole. As we drove around underneath the ice, we were actually able to track the vehicle based on acoustic pings. And through this, you can see that we were performing a loose lawnmower path, trying to map out an area. And then we found an area of interest that we wanted to explore in greater depth. Here, the color represents the depth that the vehicle is at, or in this case, actually the thickness of the ice in meters underneath that we were exploring. We went to go check out that through-hole instrument, that post that I mentioned earlier on here. And you can see that as our tail, and we're looking backwards here, is driven forward, it's not really leaving any indications on the algae. However, the act of actually deploying this instrument down here tore up the algae that it was supposed to look at. So any hope of measuring the oxygen or the salinity directly underneath the ice here was ruined by the actual input of the instrument itself. Where with the rover, we're able to place instrumentation against that under ice surface without having that massive disruption. The other thing we can do with the rover is actually turn our cameras around and look closely at the microbes, the algae that is underneath there. And here you can really see the bubbles, the oxygen bubbles that have formed over the time that the rover was down here. Now this camera can rotate 360 degrees. It's on a slip ring, so we can spin as many times as we need to. And it allows us to present our instrumentation, whether cameras or other pieces, directly at that ice-water interface. So we're within centimeters of being able to look at that ice without disrupting it compared to a larger vehicle. Over the course of our travels, we went as well up to the tidal crack. This is in some ways analogous to what we might find on Europa with the crevasses and such that can open up. And exploring that crack allowed us to evaluate the rover's ability to maneuver through the crack-like environment. And you can see even driving around, we do have the ability to get stuck on here, but with the tail, we can actually rotate it around, provide a different leverage angle, and with this can free ourselves and move along the way as well. For this particular trip, the vehicle was tethered, running essentially a network across there for higher speed video. Most of the time we actually operate just over an acoustic modem and in some ways fully autonomous, but that's what this line is extending down beneath the vehicle here. We've also been able to test this vehicle on different sizes of cracks on here. And you can see if we rotate it at an angle that we have a much better ability to cross over this. In fact, the area where we got stuck was just in the background here. So this is just further down the way, and the vehicle continues on its merry way. We ended up spending about, 3 days underneath the ice, exploring around, both local in person and remotely. The maximum endurance of the vehicle is actually able to go to about 55 kilometers of traversing underneath the ice. And the maximum time that we've spent so far underneath the ice and actively controlling it remotely has been on the order of a week. That was limited really by the fact that we had to get on a plane and head back home again. But we hope to have this explorer checking out the underside of the ice for months on end in the near future. So over the course of our travels, we were able to take measurements along the way. And this is a very interesting plot, as it's showing not only our depth underneath the ice, but mapping the conductivity of the water around us. Freshwater, it tends to be more buoyant than saltwater on here. And so as we crossed those crevasses, we actually saw that there was a gathering of fresh water up in the ice, really the melting of the outflow of the glaciers around us. And even over an area that didn't have these crevasses or these cracks where the fresh water could accumulate, we did still have some melting. And you can see that with the rover, we're able to map out very precisely how our depth of vehicle mapped against conductivity and where the fresh water was. And we could find channels of fresh water that you might not be able to see if you're just simply swimming around. So the buoyant rover provided us a new way of looking at the underside of the ice. To be frank, we invented this to begin with because we were somewhat lazy. We were up in Barrow, Alaska, and to look at the underside of the ice, we would have to cut a hole, stick a camera underneath, and look around. And if it didn't have the features that we needed, we'd have to walk a few meters, cut another hole, and repeat, and repeat, and repeat. Because of that, we came up with the idea of building a rover that could float, that could drive on the underside of the ice and explore a much wider area autonomously, returning us the data and allowing us to explore from the comfort of our Quonset hut, if not back at JPL itself. We see the buoyant rover as a novel vehicle that can explore the underside of the ice and avoid having to disturb the very environment that we are trying to observe down there because of the nature of the wheels that are always anchored on the underside and its ability to maneuver around. This particular rover will not be headed to Europa. We think it's an ancestor of one that may eventually try and get down to the surface there, but we see it as the first steps and an exploration tool that we can use to learn how to explore on the underside of the ice. And it all came because we inverted our thinking. We thought about driving on the underside rather than driving at the bottom, or how we explore around. And now it is a unique tool that we can use to learn how we might someday get out to these other ocean worlds. But this rover itself actually relies on a number of miniaturized technological components. Both the last vehicle, SpongeBob, and the buoyant rover make use of commercial parts that you can often find in the classroom or the makerspace of the hobbyist shop. And it's the miniaturization of technology from our cell phones to our laptops that really allow us to now explore with something much smaller. The question is, can these components though survive in the deep space environment? We always hear that deep space is full of radiation and temperature extremes, vacuum, and other areas that most of things like cell phones you would not expect to actually work very well. Well, at the same time that our team has been exploring with under ice explorers and deep ocean exploration, we live in an age where we're starting to look at smaller spacecraft as well. And several members of the team here, including myself, have been working on things that will get us with small spacecraft beyond our own world. And the question is, what can we learn from them? What can we learn from CubeSats themselves? So back in 2016, there was a lander that was to go to Mars, InSight. And with InSight, it was a seismological experiment to try and understand the formation evolution of not only Mars, but all of the terrestrial planets in the solar system through the investigation of structures and processes. We wanted to look at Mars quakes. We wanted to see what kind of active processes were taking place on Mars. And to do that, we needed one of the most precise seismometers ever placed on another surface. And we needed to do it without being able to touch it ourselves. So InSight was originally to launch in 2016. It ended up being delayed for 2 years. But you might imagine anytime you're going to launch something to another planet, you're launching so that you get there at just the right time. And so you're playing interplanetary billiards. Earth at launch was well away from where Mars was. And over the course of about 6 months, by the time you actually reached Mars, Mars was then behind Earth, and you had to steer yourself all the way there. Now, this total traverse is about 480 million kilometers. So it's quite a long distance. It takes about 6.5 months to get there, or at least that was the plan with InSight. InSight, eventually launching in 2018, did need to get to an entry target that was only about a little over 5 kilometers across to land specifically in an area that we were interested in exploring. So over 6.5 months, over 480 million kilometers, you need to aim for a target that's only 5 kilometers across so that you can survive the atmosphere and land precisely where you think you can make the best scientific observations on here. This period of entry, descent, and landing and getting into this target space is known as EDL, or the 7 minutes of terror. Because not only do you have to hit this very precise target and get down to the bottom, but you need to do it autonomously, because the speed of light is such that by the time you get measurements that you're entering the atmosphere of Mars, the vehicle has either survived or not and landed on the surface in one way or another over that same time period. So I'd like to talk to you a little bit about Marco and our adventures on using small spacecraft to support this much larger vehicle. And though in this case, we're not talking about an ocean world in particular, remember it's the technology inside and the ability to use commercial parts that is enabling a lot of our other ocean explorers to try and shrink down themselves and get us to another world. So this is Marco. This is actually one of two spacecraft that we were going to fly with InSight. And the vehicle here is a 6U CubeSat. CubeSats are roughly the size, in this case, or 6U CubeSats are roughly the size of a cereal box, a Sam's Club cereal box. And yet it still needs to do all the functions that a larger spacecraft might have. The heart of Marco itself was IRIS, a deep space transponder on here, a miniaturized one that allowed us to communicate back to Earth, both for command and control, as well as relaying the data from InSight as it went through EDL. And Marco had a very large reflect array antenna that we had to create that folded down to less than a centimeter in size. It had a star tracker and telescope on board, multiple antennas and solar arrays, and a host of miniaturized technology that was to enable this small spacecraft exploration on here. But it's a little hard to tell how big Marco actually was. So we like to compare it actually to things that we're more familiar with. Someday soon, we will be all able to fly again on commercial jets. And these jets are about 100 foot on a side. The typical explorer that would support something like InSight going through EDL is like the Mars Reconnaissance Orbiter. This is about half the size of a commercial jet and gives you an idea of what we would usually use to relay data back. Now, if you were going on a trip, escaping the pandemic, and taking carry-on luggage with you, and you put that carry-on luggage underneath the seat in front of you, that carry-on luggage on board that massive jet is about the size of Marco itself. Roughly 30 pounds or 13.5 kilograms, your cereal box size spacecraft is ready to go on an adventure and try and do the same things as its much larger brethren. Of course, the much larger vehicles are going to be well protected, placed in the fairing up front, if you think of your launch vehicle here. First class, if you will. Marco did not get such a ride. Marco was launched in economy class, directly next to the rocket nozzle itself for a rough ride into orbit, but by being able to place a small vehicle down here, it actually increased the efficiency of our launch. We could launch more vehicles at the same time, more explorers that we can go out to explore our solar system, which allows us to try out new things or make new observations out there. And in terms of overall cost and schedule, Marco was likewise much less expensive and much faster to create than some of these more complicated, larger explorers here. At a total cost of $18.5 million, including tech development through operations on here, Marco was minuscule compared to most of our mid-sized explorers that we might find. And it took us about 15 months to go from PowerPoint slides to actually flight readiness on here. So it's small, it's fast, and you have to accept, though, that it is also much, much, much riskier than we might otherwise launch on a regular sized NASA mission. But on May 5th of 2018, Marco launched with InSight from Vandenberg Air Force Base. And 90 minutes after launch, the Marco spacecraft deployed from the launch vehicle, opened up the solar arrays and the high gain antenna, and began its 6.5-month journey out to Mars. So with 480 million kilometers to go, our 3 spacecraft flew in a very loose formation, something like 10,000 kilometer separation on there, out towards Mars to demonstrate that the miniaturized technology that we had was going to be successful in supporting InSight and hopefully be successful in enabling more explorers into the future. For by November 26, what we needed to do was fly by Mars at just the right spot, just the right time, in order to relay data from InSight as it descended through the Martian atmosphere towards the surface, and send that data back at 8 kilobit per second, 158 million kilometers away to Earth. Now, I've been throwing a few large numbers around. I mentioned that we traveled 480 million kilometers, but at the time of actually reaching Mars, Earth itself was 157 million kilometers away. You have to love the fact that our planets are all spinning about us on here, and that orbital billiards really doesn't stop, and that we're targeting a place when we launch that isn't there yet. Mars hasn't reached that right spot. So sometimes the numbers and the times that are involved are a little mind-boggling. Now, over the course of our journey, it was anything but simple along the way, even though we had some fairly simple spacecraft. Very soon after launch itself, Marco B, our nickname for the spacecraft was Wally on here, had a propulsive leak. We started to lose fuel on a continuous basis that was actually starting to spin us in all sorts of different orientations. We had our own Apollo 13 moment, where suddenly the spacecraft was spinning out of control, the DSN was losing contact and gaining contact again, and mission directors and such were starting to encroach upon the operations room. As mission management, as we were running the team, we had to kick the mission or the program managers out of the room, focus on the problem, identify how to solve it, and we actually ended up finding a method that we could use sunlight, that we could actually use the solar wind to stabilize our spacecraft and SRP, solar radiation pressure, and allow us to continue moving towards Mars in a controlled manner on there. So in some ways, we kind of sailed to Mars in addition to using our cold gas system. And this allowed us to encounter Mars at just that right time. Now, missions to Mars are hard. The whole reason that Marco existed was because that over the course of all the missions of humanity itself, we have failed more often than we have succeeded in reaching the red planet. And so if we're going to make an attempt at Mars, it behooves us to try and observe and know what happened on there, to provide a black box of information such that if we do fail, we can improve ourselves for the future. Well, based on orbital geometry, InSight did not have that capability to send data directly back to Earth, and we needed a relay to do so. And Marco was, in essence, that relay to send that data in real time and allow us to observe what would happen, proving that small spacecraft could actually provide this capability for the future. On the day of entry, descent, and landing, Marco was a resounding success. These two small spacecraft relayed 97% of all data provided by InSight itself. MRO, that much larger spacecraft that was serving as a secondary relay in this case, only provided about 73%. We beat out the much larger vehicle because we could target exactly where to go. We could optimize where our antennas would be located in the sky to get as much data back as possible. And along the way with this real-time link, we brought 7 million people to Mars. Newspapers, articles were written about this around the world. And if you look at media impressions through tweets and clicks and other things out there, over 5 billion media impressions were made of these two small spacecraft, of this miniaturized technology that you can find in your cell phone as they went by Mars. And this is one of my favorite images because this was a photo taken by Marco B, taken by Wally as we passed by the red planet there. And it actually shows the various locations of previous explorers and how InSights landed on Mars, where Curiosity was, and even Spirit and Opportunity itself. And as we flew by, we decided to have some fun with our cameras. The image that you see before you is actually a small snapshot of Phobos, one of Martian's moons itself on there, that we were able to grab and show that these small spacecraft can do more than just their sole dedicated mission there. And even though these cameras were only supposed to be used to verify that the antennas were open, they provided us so much more in our glimpse of the solar system with a small vehicle. But Marco really wasn't only about supporting InSight. In some ways, it had a larger purpose. And that larger purpose was to show that small spacecraft could actually go beyond Earth. CubeSats could be used beyond just low Earth orbit on here. And in doing so, in traveling to Mars itself, Marco has enabled a whole host of different vehicles produced from around the world that are beginning to explore the solar system. Over the next couple of years, you'll hear of a number of different explorers that are headed out to the moon, everything from Luna HMAP from Arizona State to Lunar IceCube. We'll have NeoScout going out to explore small asteroids on here, or BioSentinel, performing experiments to look at what are the effects of the deep space environment on biological issues here. And more from universities, from government agencies, from home-built teams, such as with Team Miles here. They are putting together spacecraft to allow us to explore further with less, but with more focused experiments along the way. Experiments that, spacecraft that can hold single experiments for single investigators and such, allowing us to send more into space. And whether it's providing new vantage points of these observations, such as what Marco did for InSight, or providing us the ability to send a host of different vehicles out, creating distributed observations and allowing us to have fleets out there, or even getting down to the surfaces of those ocean worlds, disposable probes to allow for dangerous and exciting exploration. The dull, dirty, dangerous that we talk about for drones and for UAVs are now being enabled for our space exploration efforts as well, perhaps in a smarter sense, in a more focused sense than what we have attempted before. For Marco really demonstrated the necessary technology and techniques for deep space small spacecraft. It provided unique vantage points, providing more data back than what we had actually achieved with our more venerable explorers. And most importantly, it challenged the perception of what is achievable. It showed us with small spacecraft, with small explorers, we can do more, we can try more with technology that we have on hand. And what we're hoping for is this really enables us to start to explore more worlds, like ocean worlds, in more ways than we have ever dreamed possibly before. So as you grow, as you take on your experiences through Michigan Space Grants, as you try out new things out there and develop into the next generation of scientists and explorers and engineers, I hope that you remember a few of the lessons that I've talked about here in the context of ocean worlds and small spacecraft. Invert your thinking. Think about the problem from a different perspective on here. Investigate what you can do when a failure actually creates a new opportunity for you. We invented a miniaturized vehicle that had never been attempted before out of spare parts that are on board, simply because we had no other choice. And think about what you can do when you have a constrained problem, when you're much smaller, and how you can proceed along the way. Sometimes it takes a few stumbles to get yourself out and over some kind of obstacles on here, and you never know what might be feasible. But as you continue to persevere, as you continue to try forward, others will follow as well, and we will enable a new method of exploration for humanity on here. I look forward to your own explorations and what you might invent, and I welcome any questions that you might have as we continue to explore both ocean worlds and beyond. Thank you very much.
Awesome. Thank you very much for that exciting tour of Earth and space and planetary science and technology and engineering. And there's a number of questions in our Q&A box, and I'll read them to you, but encourage others to post any questions that you may have. And Katie has posted some links from Andy in the chat box that you can take a look at more detail on some of the topics that he's presented in the keynote, including more about the rover, Marco, and hydrothermal vents. So one question from a colleague, Bopi Vedanda, who's a hydrologist and geochemical microbiologist. Much of our ocean's thermal structure has been mapped using expendable bathymegraphs, XBTs, dropped from vessels that beam the data back over a thin copper filament that unwinds as the XBT drops. Is anyone at NASA thinking of dropping miniature expendable units carrying an array of sensors, including cameras, through ice fissures in Europa down into the ocean below that could stream data back to the surface lander?
Well, we have a number of challenges at Europa, and one of them is landing close enough in a safe manner that we could drop something in. But there is an exciting venture that's being worked on at the Jet Propulsion Laboratory right now, known as EELS. And this is a lander that is perhaps not as expendable as a probe as what we might use on Earth, but looks like a snake-like entity to actually go down and circle its way down into the vents itself. We're also exploring this for Enceladus on here. And by doing so, carry in various cameras and other instrumentation along the way. So it's spelled EELS. I'd encourage you to look much more at that on there and how it kind of can snake-like descend into the surface there. But we are looking at what we could use in terms of those crevasses for access down below, yes.
Great. And a earlier question, looking at the buoyant rover, when you turned the camera up to the ice and not only saw the bubbles, but also the algae, their question was on the black tags. And I assume those are algae as well, just hanging down, but if you can either correct me or.
That's right. To the best of our knowledge, those are algae as well, and they serve basically as the anchoring point there. But we see these algae have strands coming down, so it almost can capture the advantage of the nutrients and such that are passing through the salt water there as the water flow goes by.
Great. And then in terms of testing on Earth for Europa, are there any places on Earth where you can tunnel through 10 kilometers of ice?
Perhaps not 10 kilometers, but certainly kilometers of ice. And there are a number of drilling projects in Antarctica where they have drilled down to subglacial lakes and just begun to explore down there. And we actually have planetary protection concerns of those environments as well, to keep the environment pristine down below for the observations that we're trying to take.
Great. And I was in Norway in Tromsø last October. So while you were out on your icebreaker, so I should have waved a little farther north. Very cool. Another question is, could you elaborate on Marco B solar sailing,
Yep.
a spacecraft designed? How did it work to be able to correct it?
Absolutely. So we know with solar radiation pressure that this often creates a moment on spacecraft that we have flying normally based on solar arrays or any antennas on there. And so in flight, we were already having to account for solar radiation pressure to when we were desaturating our reaction wheels and such along the way. The problem, or they caused us to desaturate. The problem with solar radiation pressure in that environment was that we were having to desaturate our wheels, and we were having to do so propulsively, typically. That we would push with our thrusters, create an offset torque so that we could run our wheels down to lower speeds. Well, we didn't want to use a propulsive system that much if we had a leak on it, so we actually stopped doing that. And what we did was we let our spacecraft dwell in a number of different orientations, measured how much that would spin up or spin down our wheels, and then we learned what orientations would give us the best impact from solar radiation pressure, such that we could use that to de-spin our wheels rather than having to do something propulsively on there. And while we expected to propulsively have to desaturate our wheels every 2 to 3 days before launch, based on our use of solar radiation pressure and actually acting like a solar sail in some ways, we were able to only have to propulsively desat, I think, once or twice during the entirety of the mission. So it really was a game changer for how we could orient our spacecraft and affect the attitude on board.
Very cool. And then another question about your buoyant rover. Is anybody that's studying ice sheets, ice shelves, and biology and subsurface under ice, are anybody using your rover?
We're still looking at, we were just down in Antarctica last fall, I guess it was last winter, and working with the Australians actually to see how they could use it beyond our own engineering explorations there, but as a replacement for human divers and such. When you send a human diver down, especially under the ice, it's a massive effort requiring many, many people. And you're limited to a very finite amount of time. We're going to look at using the rover to study for weeks, if not months on end down there, and see how we can partner with their scientists to obtain the measurements that they're looking for.
Probably not as tasty for a leopard seal.
That also is an impact.
Great. Another question, just to thank you very much for your extremely interesting presentation, but could you elaborate on how the ROV was recovered after the weights were released? Was there any issue of it floating up under existing ice?
Absolutely. And that was one of the most terrifying things, because the ice above was constantly shifting with the wind. And so over those couple of days, we actually drifted tens of kilometers away with the ship and then had to work our way back to where the ROV was. And when it came up, we were extremely lucky. It came up only within about 3 meters of an ice edge. And we were not very far away from just very thick ice that even the icebreaker would not have been able to get to. And we were having to create new systems to try and go underneath, grab the vehicle and bring it back. But frankly, we got really lucky in the end there.
Great. One more question on the expedition for in the Arctic over this last winter, where they intentionally trapped themselves in the Arctic ice and circulated around. Did they use any underwater ROVs?
I don't know for sure on that one. That was on the Polar Stern.
That's right.
I'm not aware of any ROVs that they had, but I can't answer that for sure.
Great. Well, if there are any other questions, please type them into the Q&A. But that was the last question. So how often have you gone to the Arctic or Antarctica over the last few years? Has it been every season?
Certainly for the Arctic, it is almost every season, if not a couple of times. We head up to Barrow, Alaska quite a bit. And I think I added up that in the last 10 years, I've had something like 20 to 30 different expeditions to one area or another on there. I've been extremely lucky in that I've been able to do both this ocean work as well as the small spacecraft side and try and merge these two worlds on here. And I think they've both benefited from each other.
Fantastic. Well, without any other questions, actually, one more question just came in. What can you say about the changes you have been observing over the last 10 years as you visit the poles?
The one we've seen the most is up in Barrow with our colleagues in the local area up there. And many folks in that area do a lot of fishing of one kind or another. And they also have search and rescue teams. And the thing that we have discussed with them and recognized is that they are having to do more on ice rescues than they have before, because the ice is actually breaking up much earlier in the season than what they have seen in the past there. And so being in Barrow, seeing some of the Arctic environments, we are certainly seeing effects of climate change and what we believe to be more warming in that area. It's certainly a change in the dynamics up there compared to what has been historically. Not necessarily just because we're measuring the ice, but just looking at simple things like rescues and what folks are having to do.
Great. And another question came in, and we have time of, what is your prediction or thoughts on how robotic exploration will impact human exploration as we push for manned bases on the moon and Mars?
Robotic exploration has always been in service of humanity on here. And often we use these robotic explorers as precursors to head out to other worlds before humans are actually able to make that journey there. But once we are able to head out there, and just as we're doing in the Arctic, we find that our robotic brethren are able to support the exploration at hand, whether it's providing a new vantage point underneath the ice for us, even while we have our scientists around so they can identify where to drill on the ice, as opposed to making innumerable holes, or as in service of the moon, being able to allow us to scout further, to observe around. Or my favorite one is now headed off to Mars and landing in February. While we're not sending humans there yet, we are sending a drone buddy, if you will, in order to go and scout the area around it. We're going to have a helicopter flying on Mars come this spring, which will provide information back to the rover teams in there. Robots and humans are going to continue to work together. Robots are tools for human exploration here, and we should consider and continue to consider to look at how they can augment our own efforts there and work with it.
Great. And here's a a more advising question. Found your work very interesting. How would you recommend for a college student such as those attending who would like to pursue similar research?
More than anything else, keep grabbing opportunities as they come. And I know that's a very vague answer there. But I think one of the things that I found going through at least University of Michigan was student-based projects, student project teams, research projects with professors. Those all enabled more opportunities for me to explore. It took me, I think it was 8 attempts to get down to Antarctica before I finally made it there, whether it was trying to work with a professor in funding fell away or various things. But if you're persistent, if you keep chasing, and if you have a background with various projects and hands-on activities, you will find your way into these types of endeavors. And the most important thing is to keep having fun while you're doing it.
Great. And then one clarifying question. You mentioned that an AWI collaboration is at the Alfred Wegener Institute.
Mm-hmm. Exactly. They were the ones that had the OPHOBS instrument on the board and on our icebreaker expedition. And with them, we built SpongeBob. However, we ended up doing that there.
That's fantastic. SpongeBob spare parts. Yeah, awesome. Well, thank you very much, Andy, for taking your morning to share your exciting work. It was not only a very interesting, but an inspiration.